Okay, let's take a look at number 127. I'm going to look at part C, D, and E. They're all very similar. The directions here are to, given the series, either use the alternating series test to determine the series is convergent, or use the nth term test to show the series is divergent, or state that neither the alternating series test nor the nth term test applies. Now, I do have here a copy of the summary of tests for series sheet that you'll have on your test. And you can see at the very top is the nth term test or divergence test. And this test is very important because we know for any series where the terms that I'm adding up are the a sub n's, if those terms that I'm adding up, if their limit of that sequence of terms, right, is not zero, right, if they're not approaching zero, if they're not going to zero, if their limit is not zero, then the series will definitely be divergent. And the reason is, right, if you think about it, if we're not going to zero, then we're adding up an infinite number of values that are not equal to zero. There's no chance for the series to be convergent. Okay, keep in mind that just because the limit as n goes to infinity, the a sub n's, the sequence of terms you're adding up, if that indeed is zero, that doesn't mean we have convergence. So notice there's nothing here about convergence. We cannot prove convergence with the nth term test. Okay, very important. In fact, we got here as a comment, cannot be used to show convergence. So please realize if this limit is indeed equal to zero, we know nothing really, that we need some more information, right? All it means is it has a chance to converge. There are examples, for instance, of the harmonic series where the a sub n's do have a limit of zero, but yet the harmonic series diverges. Okay, so that's the nth term test. If you go down a little further, you'll see the alternating series test down here, also known as the Leibniz test. And of course, it's alternating series test because we're looking at an alternating series. Now, in general, I've written this as the sign changer -1 to the n minus 1. It could be -1 to the n. Whatever it is, that the signs of the terms of the sequence you're adding up have to change, alternate between positive and negative every other one. So this is going to do that. Here, the a sub n terms we're assuming are positive terms, right? And then the -1 will be a sign changer. So it can be either, again, -1 to the n, -1 to the n minus 1, or something like that. There's other ways to have the sign change in the series, but that's the point. But if we look at the absolute value of the terms, then just take the absolute value, we get this a sub n. Now, if that a sub n is a sequence, right? If that limit is zero, and right, the a sub n plus 1 term is less than or equal to a sub n term, meaning what? That the terms are getting smaller in value, right? The a sub n's again are all positive, as you can see here. So these two conditions, together with the fact that we have an alternating series, shows that this is a condition for convergence, right? That's what's in this column. So we know that series will converge if that's the case. Obviously, the limit of n goes to infinity, the a sub n is not zero, then we're back all the way up here at the nth term test. So you can see why number 127 is coupling these two together. Okay. So let's take a look at these three, C, D, and E. The first one is C, and it looks like this. Okay. And so you can see right away, notice it is definitely an alternating series, right? So we can see the -1, oops, I'm sorry. This is -1 to the n. So it's not an alternating series. Okay, now it is. That's what we. So that's going to change sign, right? When n is 1, we get -1 to the first power is -1. When n is 2, I get -1 squared is +1. So this little sign changer alternates between negative and positive. Everything else, if I take the absolute value and just call that the a sub n, right? That's the a sub n that we were talking about here in this alternating series test, right? The a sub n, the positive term series themselves, right? Let's take a look at them. Well, first of all, let's look at the limit as n goes to infinity. Well, I hope you can know at this point that the limit of this is infinity. Now, granted, the top is going to infinity, the bottom is going to infinity, so the form of the limit is infinity over infinity. But many of you know when you have a degree, a polynomial degree that is higher in the numerator than in the denominator, that limit will go to infinity. Now you can use L'Hopital's rule a couple times to get there. You can also divide the numerator and denominator, excuse me, by the highest degree term in the denominator, which is n squared. If I divide n cubed by n squared, I get n. N squared divided by n squared is 1. 4 divided by n squared is this. Now as n goes to infinity, this thing right here is clearly going to 0, right? And I'm left with n over 1, but as n goes to infinity, that's going to infinity. So infinity over 1 is not indeterminate, right? That's going to infinity, right? And so bottom line is you should be able to recognize that. So right away, notice it's not going to 0. So it's not the alternating series test, right? Right? But in fact, we've got a problem. This is going to infinity. What about the original, right? Which would be this basically -1 to the n a sub n. What's the limit as n goes to infinity of that? Well, we already know the a sub n's we know are going to infinity. What's this sign changer do? Well, it's going to make this limit to not exist, actually. It's not going to be infinity. What's happening is basically graphically, maybe will help visualize what's happening here. The terms that we're adding up in this series, right, are alternating, but they're getting further away from, from 0 essentially. So, maybe the first one when n equals 1 is negative, something down here. So when we're at 1, we're down here. At 2, then it's positive, but it's further away from the x-axis. At 3, it's negative, further away. At 4, it's negative, further away. At 5, it's negative, further away. As these keep bouncing back and forth, and they're getting further and further away. Now we're adding all these up, but clearly the limit as n goes to infinity of the terms of the sequence we're adding does not exist. So it is not equal to 0, right? And immediately when we have the limit not equal to 0, right, for the terms in any series, then we know the series is divergent by the nth term test. So right here, this we can say diverges by the nth term test. Right, based on that right there. Okay, now let's look at D. D is very similar to C. The only difference is instead of n cubed up here, we have n squared. You can see that there. Everything's the same. So let's look at the a sub n this time, just the positive portion, right? The rest is alternating. N squared over n squared plus 4. Now that limit is 1. Okay, well, that's better than infinity. And of course, if you don't know why that limit is 1, the degree of the top and the bottom are the same. Again, if you divide by the highest degree in the denominator, or use L'Hopital's rule, you can get there. But dividing by n squared, I get 1 up top, 1 plus 4 divided by n squared. Of course, this term here is going to 0. I'm left with 1 over 1, which of course is equal to 1. But again, if I take a look at the limit as n goes to infinity of -1 to the n, and again, I'll just call this stuff the a sub n here, a sub n, right? Then what's happening to this? What's the sequence look like here? What's this sequence here looking like, right? Well, it's approaching 1, the a sub n's, but they're going to alternate. So way out, right? Way out as we go and add the terms up, they're going to get very close to looking like 1, -1, 1, -1. They're never actually equal to 1, -1. It's like, 0.99999, but they're getting closer and closer to 1, right? Because of this limit. And so, but the problem is, right, we're not going to settle down to anything here because we keep getting 1, the even terms maybe are approaching 1, but the odd terms are approaching -1, or vice versa, depending on the, I guess here we can tell, right? It says odd ones are going to be negative. So the odd ones are approaching -1 and the even ones are approaching +1. So again, this limit does not exist. We're just bouncing back and forth. It's like this one here, except we're not just going away. We're bouncing between -1 and 1. And so again, the limit though of that sequence does not exist. So it is not equal to 0. And so this one here diverges by the nth term test as well. So C and D both diverge by the nth term test. Now E is a little different. Notice the difference now from n. We had n cubed, n squared, and now we just have n. And if I take a look at the a sub n now, the limit as n goes to infinity of n over n squared plus 4 is equal to 0, right? So now the question is this the alternating series test? Because that was one of the conditions, right? The limit has to be 0. Well, is this also true? Is a sub n plus 1 less than or equal to a sub n. Okay, and again, I'm calling the a sub n the n divided by n squared plus 4. Okay, so is this true? Is it decreasing? I think most of you can probably ascertain that it is, and there's a variety of ways we can do that. One way we can do it, right, is to show that the function is decreasing. It doesn't have to be decreasing for all values of x. You know, I'm doing x here instead of n. I could just do it in terms of n, but right, it just has to be for some point after 1, right? This starts n equal 1 to infinity, but some point of this function has to be decreasing. So how do I know if a function decreases? By looking at the derivative. So I can find the derivative here by the quotient rule. If you remember that, the derivative top x is 1 times the bottom minus the top times the derivative of the bottom. Derivative of x squared plus 4 is 2x over the bottom all squared, right? That's the quotient rule. Up top, if I simplify, I've got 1x squared minus x times 2 minus 2x squared. I get negative x squared. All right, negative x squared. And then I get plus 4. Or let's write it this way: 4 plus a negative x squared, or 4 minus x squared. Okay. Now, take a look at this function, the derivative now. When is the derivative positive and when is it negative? Well, the denominator is always positive, right? X squared plus 4 is always a positive number. And then when I square that, of course, it's still going to be positive. But 4 minus x squared, if I were to look at a sign check of just that part, right, then we know at both -2 and 2, of course, we're not really interested in negative numbers since we're starting with n equal to 1. But, right, here's 0. But any value in between -2 and 2, if I plug into 4 minus x squared, I'm going to get a positive value. At 2, of course, it's going to be 0. Of course, at -2, it's 0. Any value greater than 2, if I plug in a value greater than 3, like 3, 4 minus 3 squared, 4 minus 9 is -5, right? So the top is negative, the bottom is always positive, so overall it's going to be negative. But this is telling me that this thing here is going to be less than 0, is going to be negative for any value of x that is greater than 2. Okay, and I've just changed the variable from n to x here. I mean, I could have left this all as n, and that's fine. Then what we're saying is this sequence of terms, this statement is true for what? For n being greater than 2, because we know for values greater than 2, then this function is decreasing. And so these terms in the a sub n's that we're adding up, they are decreasing. So we have this condition is satisfied, we have this condition satisfied, and therefore, by the alternating series test, this series converges. Converges by alternating series test. And I've explained both these two important pieces, right, that are required, right, to show that we have convergence. Okay, so there is a good contrast of using both the nth term test and the alternating series test.